Hey everyone, welcome back to the second tutorial on creating an xHCI driver from scratch. So this is the point where we left off in the last video after getting the basic setup up and running with our two little prints here. And if we look at the code, we have our two main files here, xhci.h and xhci.cpp. Now in addition to those, before recording this video, I also added a file called xhci-common.h, which just contains a ton of useful macros, definitions, and above each one references to the official xHCI spec, section and page numbers, and explanations straight from the spec for each of the macros. The link to the GitHub repo for these tutorials is always going to be provided in the description, but I'll also additionally leave a link to this file specifically, so you can just easily copy paste it into your project. These macros will be really useful and come in handy throughout the whole series, so we'll definitely need this file. Make sure to copy it into your project. First, before jumping into any code, let's go over what we're trying to do and why it matters. In a typical system, you have two major memory regions to worry about. The kernel's memory space, which the OS normally uses, and the PCI memory space, where PCI devices store their configuration and control registers. In our case, the xHCI controller, the part of the system responsible for USB communications, resides inside that PCI memory space. The kernel can't directly read from or write to that space unless we create a mapping. So how do we do that? We allocate and set up a window, a small slice of the kernel's address space, that directly points to the xHCI region in the PCI memory. Once that mapping is in place, the kernel effectively has a direct line to the xHCI registers. It can read them to check the controller's status, or write to them to tell the controller to perform certain actions. This entire process is crucial because without that mapping, we'd have no way to configure or interact with the controller. With that foundation in mind, let's jump back into the code and start implementing this. Alright, so the first thing that we need to do is map the xHCI controller's PCI memory into our kernel's virtual address space. And for any memory-related functions, let's create a new file, xhci-mem.h. First, we'll include xhci-common.h, and let me also include my kernel's memory header files. I once again prepared a list of useful macros and defines constructed straight from the information in the official spec, describing the sizes, memory alignment, and boundary requirements for various components of the xHCI controller that we'll go over when we get to them in the upcoming videos. We'll go over each and every one of them when we get to them, but for now let's just keep them in the memory file. Alright, let's now define a few memory-related functions that our driver is going to often use. First, obviously, we need a function to actually map the xHCI controller into our address space. And it'll take a PCI bar address and the bar size in bytes. Next, we'll need a function to allocate xHCI compatible memory, which will require a DMA allocator, which I'll assume your OS has at this point. This function will take the size of the allocation, an alignment requirement, which by default let's make 64 bytes, and a boundary requirement, which by default will just be one page. Then, naturally, we need a function to free our DMA allocated memory, which just requires a pointer as a parameter. And finally, we'll create a wrapper function to convert a virtual address to a physical address, and since the xHCI controller will often require and work with these physical addresses. Again, I am creating these functions more to provide you with a chance to use these as wrappers, and if your OS uses a different implementation, or at least the rest of the code can stay consistent. Great. Let's first now implement xHCI map MMIO function. For this, we'll first calculate the number of pages that the controller will take up, which is just our PCI bar size divided by the page size, which by default is 4K. Next, I'm going to invoke my virtual memory manager to allocate contiguous physical pages for the controller. Ensure, this is important, the pages have to be contiguous. The physical pages have to be contiguous in memory. Here we'll pass in the PCI bar address as the starting address, our calculated page count for the count, and we also have to make sure that the memory, when we map it, is marked as page cache disabled. Then we're simply going to return the mapped address casted to an uint pointer. Great, now that we have that implemented, let's build our xHCI memory allocation function. First, let's implement just a few simple checks to make sure that we provided valid inputs for the size, alignment, and boundary parameters. If any of these are invalid or 0, for now we'll just throw our driver into an infinite loop. We'll deal with proper error checking and logging in the later videos. If all our inputs are valid, we'll simply call the DMA allocator routine to provide us with an appropriate memory block. Again, this implementation may differ for your OS, but I have a DMA allocator with this API that I'm just going to call and get a memory block back. We then have to check if the memory block is valid or not, and if not, once again, just throw our driver to spin forever. But if it's a good block, we'll mem set it to 0 and return the allocated pointer. Now, the free xHCI memory function is going to be super simple and just simply take the same DMA allocator as before and call its free function on the provided pointer. Finally, the xHCI get physical address function should also be very simple and straightforward, and assuming you have one, call a paging function to convert a virtual memory address to a physical memory address, and simply return it. And that's it for our xHCI memory file, at least for now. So now that we've got our memory functions done, let's test it out. First, let's create a variable to store our mapped controller base address into. Then let's go into our init device function in the main driver class, and I already have it in my parent PCI device driver class, but you'll need a way to access the controller's bar base address register here. Even if it has multiple bars, you typically just need the first one, bar 0. So here I'm going to get the PCI bar struct out of the protected variable mPCI device that I have, and we just need the first one, so at index 0. Now let's quickly go back into our header file and actually include our xHCI mem.h file so we can call the mapping function or our init device. And let's call xHCI map MMIO and store the result in our newly created variable. Now to test this, if it worked or not, let's just print the result and see what our virtual address for the controller's base is. And now actually at the same time, we can also test our virtual to physical address conversion function and see what the mapped physical address for the controller is. On QEMU, it's typically going to be something like 0x8000 and a bunch of zeros. So let's run this now. Let me exit out of the previous QEMU instance here and recompile the project. Great, looks like it compiled successfully, so let's run it now. Wait for it, and beautiful. We got our host controller base virtual and physical addresses here, and if we look at it, the mapped physical address is indeed 0x8 and 8 zeros. And the virtual base address looks pretty solid as well. Amazing. Now that we can actually access the host controller's memory, we can do interesting and fun things like actually read the different components of what's called xHCI memory space. And one of the first things we're going to read is the capability register space. Before we continue, let's take a closer look at the xHCI memory space. It's divided into several distinct register sets, each serving a different purpose. First, there are the capability registers, which describe the capabilities of the hardware, details like the length, interface version, and various structural parameters. These registers help the software understand what features the controller supports. Next, we have the operational registers. These are like the control center for the controller and can be used to reset, start, shut down the controller, or read what state it's in, for example. And then we also have other register sets like the extended capabilities, runtime, port, and interrupt management registers. Each of these play a different role at different stages or aspects of device connection, port, or event management. For now though, we'll only look at the first two, the capability and operational registers. These two groups give us a clear view of both what the controller is capable of and will soon be used to reset the controller. I'm not going to go through every field right now, but I'll just quickly mention the fields that are most relevant to us at the moment. The cap length field is used to determine how long the capability register set is in memory and determine the offset for operational registers. Now these next two are offset fields that are in the future videos will allow us to find the offsets to the doorbell register array in the runtime register set. Don't worry about them too much right now though. Moving on to the USB command register. It's used to transition the controller into different states, for example halt or start the controller. It also could be used to enable or disable controller interrupts. USB status register will also be really important, as it will allow us to read any potential controller errors or status of various operations. I'm not going to go into too much detail about the next two right now, but CRCR, or Command Ring Control Register, will allow us to set up and enable a command ring, over which we'll be able to send actual commands and request packets to the controller. Finally, Device Context Base Address Array Pointer, I know, a lengthy name, will allow us to set the buffer where USB device context will be stored. Again, don't worry about these too much right now, we'll cover them all in greater detail when we get to them. For now, let's get back into the code. Alright, so what we're going to do now is create yet another file called xHCI regs.h. This file will contain all of the different register space definitions for the xHCI controller. Since all of this is just taken straight from the xHCI spec, I'm just going to let you watch a nice relaxing time lapse of me typing out all of these struct definitions. Enjoy. And boom, there you go. We have our first register definitions. We only have two now, but believe me, we're going to add a lot more to this file as we progress and develop the driver. Now, let's go back into our main driver code, and let's first include the regs header file. Now we'll create a volatile instance of the capability and operational register sets here, and it's really important to make sure these are declared as volatile to avoid the compiler optimizing out reads or writes from these, as the controller can change or modify values behind the scenes. So we always need all the reads and writes to go through memory to avoid caching behavior. Now we will declare a set of variables to track the controller's configuration information. We will retrieve values for these from the different bits of the capability register set. These will include things like the length of the capability register set, maximum number of ports, device slots, scratchpad buffers, different capabilities, etc. Right now, these probably sound very foreign and weird to you, but soon in the upcoming videos, we're going to cover each and every one of them, and all the different parts will start to click together, I promise. So now, let's also declare a couple private functions here. First, to read and parse the capability registers, and another also to just log or dump them for testing sake. If we now go into our CPP file, let's create these function definitions, and first implement parsing the capability registers. Let's first assign the cap register variable to the controller's base address, since they start at offset 0. For the capability register set length, that will simply be the cap length field. Easy enough. Now for the next values like max device slots and so on, we're going to use the very useful macros I mentioned earlier in the xHCI common header to extract the necessary bits from the appropriate capability register set fields. There's nothing deeply conceptual to memorize here, so just taking the information from the official spec and reading the right bits into the code, so that's why I provided the common header to make your guys' life easier. So let's do it for the rest of the values real quick. Great. Now we're pretty much done with the capability registers. Now in order to find the offset of the operational register set, we simply need to add the cap length field that we read earlier to the controller's base address. Great, so the only thing left to implement here now is the logging function, which I'm not going to make you sit here and wait for me to type all the boilerplate code out, so I'm just going to copy paste this from the side. Here you go. Finally, after we have mapped our controller in the init device function, let's call the new functions to see what we read from the controller. Let's recompile the project again. Great, and let's run this. Beautiful. We can see that what we've read from the controller is some pretty important and cool information, such as it's not using the 64-byte context size, it's capable of reading and writing 64-bit addresses, controller is not using any scratchpad buffers, and there's 64 device slots, and it has 8 ports, so a maximum of 8 devices can be connected to this controller at the same time. If you've made it to this point, congratulations. You've successfully mapped in and read some pretty cool information from the xHCI host controller. That's not a small feat, congratulations. This is just the first stepping stone in a long but really fun journey of getting USB support working, and I hope to see you all in the next part, where we start to reset the controller.